Hello guys, welcome back to Stat 3617. I hope you enjoyed the online learning so far. Last week we talked about how we make use of the simple random sampling scheme to estimate the population mean, population total, and the population proportion. We also estimate the variance. Using the variance, we can construct the 95% confidence interval for our point estimate. We also discuss about how we determine the sample size little n with the required bounds of error or required precisions. This week I'd like to talk about some other estimation method like the ratio estimation. Let's look at this example. The wholesale price paid for oranges in large shipments depend on the sugar content of the load. Then we need to determine what's the total sugar content of the load. First, we can estimate the mean sugar content per orange, which is μy. Then we multiply the number of oranges, n, in the load. This is one way of estimating the total sugar content in the load. We can conduct a sample survey, just collect n oranges from the load, taking the sugar contents together, take an average. With the y bar, which is the unbiased estimator for the population μy, then multiplying that y bar to total number of oranges, we can find the total sugar contents tau hat. This method could be problematic somehow because we usually don't know how many oranges in total in one shipment. Alternatively, we can make use of some other information that is available for us in the population or in the sample. For example, we know that the sugar content of the orange, yi, could be closely related to the weight, which is x. So if we have this additional information, we can make use of this information to enhance our estimation of y. Looking at the ratio of the total sugar content tau y to the total weight of the truckload tau x, and that equals to the ratio of n times μy divided by n times μx, cancelling the capital N, the ratio would equals to μy to μx. Putting that tau x to the right-hand side, the total sugar content of the shipment could equals to average sugar content to the average weight multiplied to the total weight of the shipment. The tau x can be easily obtainable because we can weigh the total load or total cargo of the shipment. μx and μy we can obtain from our simple random sample. We can estimate μy by our sample y bar. We can estimate our μx by our sample x bar. Now we can have the estimated total sugar content of the shipment by using this ratio multiplied to tau x. Or we can multiply that by n. We can also use the total sugar content in our sample to the ratio of total weight in our sample multiplied to the true value of the weight in the shipment to do the calculations. So this is called the ratio estimator. Using ratio estimator, we assume R, which is from the population, equals to tau y to tau x, or y bar to x bar in the population. If we look at our sample, we can estimate our y bar to the x bar, which equals to our sample R. We say that sample R could be an unbiased estimator for the population ratio. So we are saying expected R is the unbiased estimator to the population ratio, and that could serve as a ratio estimator for us to estimate the y bar in the population. I have written down some written notes to further explain about that. Okay, so in the populations, we can find some supplementary informations like xi, yi. They are highly correlated variables, so they comes in pair x1 yi, x2 y2, xn, yn, they are linearly correlated, then we can say that in the population ratio, R could be expressed by the population y bar to the population x bar. If I move the x bar to the left-hand side multiplying to R, we can find the relationship between the y bar to the ratio multiplied to x bar. Now, if I don't have all the information from the populations, I'm going to take a sample out of it. In the sample, I could also obtain a set of the xi, yi, up to our sample size n. And then we can obtain our estimate R from our sample y bar to the sample x bar. We are saying that little r is an unbiased estimator for the population R. If I can use this relationship from the sample, assuming R is an unbiased estimator for this capital R, then I can multiply this with the true value of the x bar to obtain the unbiased estimator for the population y bar. You can see that this y bar, I have a little r to indicate this y bar is estimated from the ratio estimation R, but not the ordinary way, which is adding up all of the yi divided by n, same as in my sample. Okay, so in my sample, usually the original way, or the ordinary way, is to use my sample y bar, which is the average of all of the yi. I use that to estimate the capital Y bar. But now I'm using a ratio estimation, which is I rely on the little r that I obtained from my sample y bar to x bar, multiply to the true value of x bar, a capital X bar. Now I use this relationship to estimate the y bar. In this case, y bar is obtained from the ratio estimator. Now, from the ratio estimator, we have the expected value. We also want to define the variance of R. What is the variance of R? Let's take a variance on both sides of these equations. Okay? Variance of y bar R equals to variance of R x bar. X bar is a constant, so variance of x bar becomes x bar squared taken out of the variance. So if I'm trying to put it this way, the variance of R would equals to 1 over x bar square multiplied to variance of y bar R. Do you see that? Okay, this is a constant. We can easily obtain it from the population. So just keep this constant. Variance of y bar, we learned it last week. We can find that equals, under the finite population assumption, that equals to the finite population correction factor multiplied to sigma r squared over n. So sigma r squared is defined as the variance within the r, within the yi to rxi. Okay, so now the variance of r depends on the variation of yi and also the variance around the rxi. If sigma r squared is given, then we can substitute this value into here, and then we can find the variance of r. Again, if sigma r squared is not given, is unknown, we use our sample as r squared to estimate our variance of r. Okay, estimating the variance of r, so we had a hat on top, copying the same constant, 1 over x bar squared. Now we have estimated variance of y bar. Using our sample variance SR squared, so we have another finite population correction factor, multiply SR squared over n. SR squared would become the variance around our sample linear relationship between the yi minus rxi. That becomes our equation 3.25 and 3.24 in our text. Okay, So this is the text. You can read that through, or the example that I just talked about, population R and our sample R. We say that our sample is an unbiased estimator for the population R. We just define the formula for variance of R. We have equation 3.24, and if sigma R square, this is sigma R square, if this is not known, we estimate it using SR square. Okay, in the text, what I'm trying to say is I expand this square bracket like a minus b, so it becomes a squared minus 2ab plus b squared. So nothing too tricky. In the estimate variance of R, we have SR square. SR square is taking the variance within our sample. Okay, so we have n minus 1 in the denominator. Expanding this square bracket, we also have a squared minus 2ab plus b squared. This is equation 3.26. Okay, and if we can relate, if you can record, that's the variance of sy squared and sx squared and the covariance of sxy, and also the correlation formula rho equals to sxy over sx over sy. We can substitute everything in here into the formula 3.26, and we have another expression 3.27 for the calculation of the estimated variance of R. Okay. One more thing, in the text, I have 1 over mu x squared. It's just the same as what I'm showing here. 1 over capital X bar squared is the same thing. Okay, so I'm showing different formats of the equations so that we can do the calculations depending whether we have this information on hand, or we have the summary of the data on hand, or we have sy squared, sx squared, r squared, etc. All these variables available for us to substitute into your choice of equations to find the variance of R or estimated variance of R. Okay. Very quickly, I tried to show how we arrive at the equation 3.27. So this is SR squared. Okay, so expanding SR squared, we have equation 3.26. We know R equals to y bar to x bar. Put it this way, y bar minus rx bar will equal to 0. If I take a square, multiply to n, it's also equal to 0. Okay, so if I substitute this bit into this bracket, so let's say within this bracket, I subtract n bracket y bar minus rx bar square. It doesn't change my value. Okay, so subtract this thing so that I can have summation of yi square subtract ny bar square, and I also have r square multiply to summation of xi square minus n x bar square. So I have this bit, and also the one in the middle. Okay, so you can read that through. In that case, I still have n minus 1 outside. Okay, so this bit divided by in minus 1 is indeed sy squared. This bit divided by n minus 1, I have r squared sx squared. This bit divided by n minus 1, I have this. So that becomes 3.27.